Today I'm going to change the focus away from rotational motion to the next issue of periodic motion we would like to investigate, and that is wave motion. I think when I say waves, it evokes in your mind images of particular things, but I think most often in the mind of the student would probably be ocean waves. And if you think about it, ocean waves, dreaming of going to the shore when all of this is done, ocean waves come periodically, a certain amount of time, one wave and then the next. That's sort of a life experience that everybody has, but we haven't thought about it in a physics way. So what I'm going to do is take something that's very familiar, like waves on the ocean, or slightly less familiar and a little bit more sciencey, waves in the air that we call sound, and something completely abstract, waves of electromagnetic radiation that we call light. And I'm just going to physics it up a little bit and talk about it in a more formalized way and see if we can draw any new conclusions beyond what we experience in everyday life. Vibrations are periodic motions that are localized in space. Anything that vibrates. That really isn't a scientific word. Vibration is a thing that happens all around. It's a thing that's a little bit springy, and you give it a tweak and it vibrates, like a ruler on the end of the table, or a spring. Vibration is a periodic motion that remains localized in space. If I take a mass and I hang it from a spring, it doesn't go anywhere, but it bounces up and down. But it stays in this general location in space. Waves are also periodic because they're caused by vibration. For example, if I had a tank of water that was perfectly calm and smooth, and I poked my finger into it periodically, that is with a certain time period or frequency if you like, it would create waves. Everyone knows this. But the waves aren't localized. They travel away and away and away and away and away. And so I go for a hike and there's an enormous pond and it's very, very calm, very calm morning, and I throw a pebble. The pebble strikes the surface of the water, and away from that disturbance travel undulations in the surface of the water. And they travel and they travel and they travel and they travel, and perhaps it would be forever until they reach the shores, where there's a barrier that stops them. Vibrations are periodic motion that remains localized in space. For example, our pendulums that we've already studied. A pendulum swings back and forth, but it doesn't go anywhere. Neither does a mass hung from a spring. It'll just bounce up and down at a certain location in space. But waves are vibrations that travel. My go-to examples are waves on the ocean, as I've said, but light. We see light in the sense that it goes into our pupils, stimulates our rods and cones, and creates a nervous sensation in the brain. But we don't see the light traveling by us the way we do a water wave. Nevertheless, in this room right now, we're awash in light from the light sources on the ceiling and coming into the window, and even invisible light that we ourselves radiate because we have a body temperature, and every hot object in the universe emits light. It's just light with a particular energy that we can't see. Light is a periodic phenomenon and a wave. So is sound. Can't see the vibrations of sounds necessarily, although there are ways to visualize them, as there are for light waves, come to think of it. I can't see the vibrations of sound, but sound travels through space, and light travels through space in the form of waves. Here's a little bit of visualization, an explanation of what I mean. Here's a tube that presumably is full of air. And what happens is you take a tuning fork and you bang it on something. You hold the tuning fork up to the end of the tube. Now, the tuning fork doesn't go anywhere. It vibrates. And the vibration of the tuning fork pushes on the air inside the tube. But it doesn't just give one push. It gives a push and then a pull and then a push and then a pull and then a push and then a pull. And the air inside the tube vibrates in a vibration that travels. Now, my still image here on the screen is not animated. If it were, we would see, for example, this point here on the left where there seems to be a very tight concentration of air molecules that would travel across as the wave propagates through space. Sound waves in the air are created by the vibration of the tuning fork. My voice, sound of my voice, is created by the vibration of my vocal cords. My vocal cords vibrate like a tuning fork. They push and pull on the air. That push and pull pushes and pulls on all of the air from me to you. It travels from me to you, and then it hits your tympanic membrane inside of your ear, which stimulates some nerves, which then sends a nervous impulse into your brain, which you interpret as sound, the experience of sound. Here is an antenna, like a radio station antenna. It's far more difficult to visualize. But inside the antenna, there are fundamental charged particles called electrons. And the folks at the radio station cause those electrons to wiggle up and down. And when they do, they create an influence in space that travels across the land to your car's antenna, where it runs into other electrons in the antenna and causes them to vibrate. It's the vibration of electrons in an antenna that creates radio waves, which are the same type of electromagnetic radiation as light waves are. The thing about waves is that they transfer energy through space. You know what I'm going to say? Shadi, what do you mean energy? I mean in the compression and rarefaction of the air in this tube, there's a number that you can calculate. There's an equation for it. That is the energy of the wave. There's an equation for wave energy. It exists. I didn't put it on the slide because that's not my issue for today. But there's a number that you can calculate that is the energy. And when these radio waves that are vibrations of electric and magnetic field travel through the air to communicate messages, there is a number that you can calculate associated with the electric and magnetic fields of a wave that is the energy of the wave. It is the energy that is transferred through space. In the case of sound waves, it's the energy, not the air. In order to speak and make a sound that you can hear, I have to inhale, and that requires muscle. Where do I get the energy to do that? Well, from the breakfast I ate. It's metabolic energy. I use metabolic energy to draw air into my lungs and then compress it. The force of my lungs compressing is work over distance, right? A number of joules of energy. Those joules of energy vibrate my vocal cords in my throat. That energy is kinetic energy as my vocal cords vibrate back and forth. And then my vocal cords push on the air and pull on the air, push on the air, pull on the air, doing work. But the air from my lungs does not travel to you. Good news there, I guess. Eat a lot of onions and then give a lecture. No, the air from my lungs does not travel to you. Only the vibration does. And what the vibration brings with it is the energy of the vibration, not the air itself or the electric and magnetic fields themselves, or even the water itself. I know you appreciate this, but when you're on the East Coast enjoying a day at the beach and the waves are coming in, that is not water from England, because it's not the water that moves. It is the disturbance that moves. Oh, but I get knocked over by the waves. Yes, because those waves have energy. What do you mean energy? Associated with water waves, there's a number that you can calculate, which is the number of joules that are in the wave when it arrives, and it delivers that energy and knocks you on your butt as you're wading around in the shallow at the beach. Vibrations have an amplitude. The term amplitude is critically important and applies to all vibrations. Amplitude simply means how far from the equilibrium position. So for a pendulum, the amplitude is how far do I pull it to the side before I let it go. For a mass on a spring, the amplitude is how far do I pull it down before I let it go. For a wave, the amplitude of the wave is how far it goes above or below, same distance, the equilibrium level. Ocean waves, for example, if you're out in the ocean with your swimmies on, The ocean wave comes by and you go up, but then you also go way down and then come up again. Somewhere in there's a middle level. The amplitude is how far above or below. The amplitude is the maximum disturbance. I just improvised that right now. The amplitude is the maximum disturbance. I think I would have typed it on the slide had I thought of it. The amplitude is the maximum disturbance. Now, waves are periodic. You can see here that it looks like a cosine function or a sine function that I encountered in math class, and it repeats over and over and over again. Repeat, 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 repeat. It's periodic. There is a particular distance in space, a particular number of meters from the peak to the peak. The peak-to-peak distance is referred to as the wavelength of the wave. It is easiest to see when you look from peak to peak to see the wavelength. But it's the same distance as from the trough to the trough, or from any point on the wave to the identical point in the sequence. The wavelength is well named. It is the length of the wave. So I go out and I start experiencing some waves, water waves, sound waves, waves on a rope, electromagnetic waves, all these different kinds of waves. And imagine what it's like to see a wave moving by. Well, I think the visualization will work best for us with these water waves. So here we have some kind of a bird. Doesn't really look like a seagull, but it's standing on a pylon here and watching some water waves go by. Very curious seabird. The seabird makes two measurements of the waves. First of all, that they're traveling at 4 meters per second. You might not have thought of it, but it's true. You go out on the jetty and those waves go by, you could, with a stopwatch, say, well, it travels a particular distance in a particular amount of time, and that is the speed of the wave. The same way that I calculate the speed of anything. How far does it go in a certain amount of time? So let's say that these water waves on the ocean happen to be traveling at 4 meters per second. Very clever bird here measures that the distance from peak to peak on the wave is 2 meters. That is the wavelength, represented by the lowercase Greek letter lambda. On the previous slide, I didn't make a bunch of noise about how I keep using these Greek letters. I can't use W for wavelength, can I? That would be confusing. So I use lambda, which is sort of technically not exactly the Greek L. It's not really, because it's not even the same number of letters, different language entirely. But la lambda for la wavelength, or wave la length. Makes sense. The Greek letter lambda, the wavelength here, 2 meters long. So if speed is the distance over time, boy, that's trivial physics. The distance that I'm talking about when I'm talking about waves is the wavelength lambda. And the time that I'm talking about is the periodic time. It's the time for one go-round, for one cycle. Periodic motion is what this unit is all about. So the time that I'm talking about is the time for one cycle is capital T. So the wavelength, 2 meters, divided by the wave speed, 4 meters per second, gives me a time period of 0.5 seconds. I can work out the time period of this periodic motion. Time period is simply related to the frequency because the frequency is 1 over the time period. So if the time period is 0.5 seconds, then the frequency would be 1 over 0.5 seconds, would be 2 hertz. The wave has a frequency of 2 hertz. There is an equation that is used every time waves are an issue, in every aspect of our science, engineering, biology, everywhere. Very famous and important equation. The wave speed is equal to the frequency multiplied by the wavelength. Shadi, why don't you do it as the wavelength divided by the time period, the way you just did, lambda over capital T. Yeah, I can do that. It would be totally equivalent. Partly, this is traditional. Actually, I would say mostly it's traditional to write this equation in terms of frequency instead of time period. Remember that my chief reason for using frequency to describe periodic phenomenon is when the motion repeated itself many times in a second. That is, when the oscillations are fast. When I'm talking about sound waves, for example, it would be very common to encounter a sound wave that had a frequency of 440 hertz. That means it wiggles 440 times in every second. It's more convenient to talk about sound in terms of frequency than it is to talk about it in terms of time period, even though those ideas are just reciprocals of each other. So we write this very important equation, and we're going to do calculations with this, not only in this unit, but in future units as well. It's a very, very important and valuable equation. The speed of a wave is equal to the frequency of the wave multiplied by the wavelength. There are many different ways to categorize different kinds of waves that we encounter in our science. But that would not be a very interesting course of study for us to do. But I do want to mention one way of classifying our waves into two possible kinds of waves. I already mentioned the waves in the air. I had an image of a tuning fork, and the tuning fork pushed and pulled on the air. What we have here in the diagram for part A is a person using their hand to push and pull on a slinky. Pushing and pulling on the slinky causes the slinky to compress, and you can see there are regions along the length of the slinky where the coils of the slinky are closer together, where they compress, and then there are regions where the coils of the slinky are more widely separated. I'm not even going to put it on a slide or require it at all, but that is actually, we have compression. The stretching out is actually termed rarefaction, which is a strange word. Compressions and rarefactions. Compressions and stretches. In the direction that the wave is traveling. Waves that vibrate in the direction that the wave travels are called longitudinal. A familiar word because the vertical gradations on the globe of the Earth are called the longitudes. Vibrations in the direction of travel make that a longitudinal wave. But here, same slinky, but in this experiment, in diagram B here, the student wiggles it back and forth, moving the slinky perpendicular to the direction the wave will actually travel. Such waves are called transverse waves. And in the course of this discussion, I've already given you two excellent examples. Sound waves are longitudinal waves. They're push-pull waves. Light waves are up and downy waves. Wiggle-wiggle waves. Never did I need a scientific word more than now. Transverse waves. Transverse meaning they oscillate perpendicular to the direction that the wave travels. All caught up. Huzzah. Happened all of a sudden. You didn't even know that was going to happen. I thought it was going to last forever. I kind of like that little bit that I click a button and all of a sudden everybody's like, oh shit, it's over. You all right? All right. Fantastic. Whew. That was all right. That was not my best performance, but I think I'm going to keep it anyway.